often we think of differentials in terms of errors. And so I want to take a look at an example where we can understand how differentials can be used to approximate error, and also where we can get a nice visual representation of what the differential of a function looks like. Okay. So let's suppose we were trying to manufacture rectangles whose dimensions were x units long and y units high. I'm going to keep it sort of generic for now. We might, of course, have specific dimensions that we were shooting for. Now, the area would then just be x times y. So area is a function of these two variables, x and y. And I'm just going to call it a rather than calling the output z, because there aren't any z's when I spell the word area. Okay. All right, so x and y are representing the dimensions that I want to get. But anytime I measure something, there's a chance that I'm going to measure it a little bit wrong. Okay. And so there could be some error. I could be off a little bit from the x value that I was trying to get. So that would be my delta x, which would be the same as my dx. Now I'm going to draw it as if dx is a positive value. So I measured it just a little bit too long. Differentials are signed quantities. They can be positive or negative. And error is a signed quantity. It can be positive or negative. It's just a little bit easier to visualize if it's positive. So I'm going to go ahead and do that. And then if I measure y a little bit wrong, the error in y would be my delta y, which would be the same as my dy. Again, I'm going to draw it with dy being positive, just making a mental note that both of those differentials could be either positive or negative. When I make a mistake, I don't always measure things too big. Sometimes I make them a little bit too small. Okay. All right. So if I take a look then, I was trying to get this rectangle, and what I actually got was this rectangle. So I can see that what I'm shading here in yellow doesn't show up super well, but we got it there. That's my delta A. That's the actual error in area. If I measured x too big by this much and y too big by that much, I would have the area too big by that amount that's shaded in yellow. Okay. But what does the differential look like? Because I could say that delta A is approximately dA. And so then I'm interpreting this as the error that I got in the area. And that would be the induced error from the fact that I made a mistake in measuring x and I made a mistake in measuring y. Okay. Well, I know that this would just be the gradient of A dotted with dx dy. The gradient of A, that's just going to be the partial of A with respect to x, comma partial of A with respect to y, dotted with dx dy. If I wanted to, I could write A sub x and A sub y here. That would be fine. Let's see. That is going to be just y is the partial with respect to x. The partial with respect to y is just x. And then we're dotting that with dx dy. So we're getting y dx plus x dy. Well, if I take a look over here, this rectangle right here has as its dimensions y times dx. And this rectangle up here has as its dimensions x and dy. So dA is what I just shaded in blue. It's approximating delta A, which was everything I shaded in blue, plus this little bit that's yellow but not blue. Okay. So I can actually see dA does a pretty decent job of approximating my delta A, and that would be my error that I have. Now, sometimes you're asked to approximate the maximum error that you could have. Okay. And the book doesn't do a really great job of acknowledging that error is a signed quantity, and that when you're sort of looking at the maximum amount of error, you're looking at the absolute value. Okay. So error, if I were looking at area and I had 2 square inches, positive 2 square inches would mean I was 2 square inches too big. Negative 2 square inches would mean I was 2 square inches too small. But sometimes we just talk about how much were you off. That would be the absolute value, and that would be the 2 square inches. Okay, so let's just take a look at this one. Okay, so using area, which is x times y, let's suppose that we were trying to get something where x was 3 and y was 5. That would mean, of course, that our target area was 15 square units. Okay. And let's suppose that we know that the absolute value of dx is less than or equal to 0.1. What that's saying is that the error in x will be no more than 0.1. Okay. Now, the book just says that in words, and they say x is accurate within 0.1 units, whatever the units are. Let's say inches, within 0.1 inches. I kind of like to write the absolute value because that reminds me it could be 0.1 inch too big, it could be 0.1 inch too small. Error is a signed quantity, but often we're just concerned with how much error there is. There are times when we're concerned about what direction that error is in. Okay. All right, and let's suppose that we know that the absolute value of dy is less than or equal to 0.05. Somehow whoever's measuring the y is a little bit more accurate than who's ever measuring the x. Okay, if we're asked to approximate the maximum error that we can have, we're basically looking at what's the absolute value of dA. Okay. Now, we calculated our formula for dA a moment ago, and that was just y dx plus x dy. Okay. All right. And so in this case, we're taking a look at the absolute value of y was 5. Dx, well, we're sort of told that the worst case scenario is that dx could be 0.1 or negative 0.1, but that its absolute value would be 0.1. So when we're approximating the maximum error, we're going to just assume worst case scenario, and we're going to plug in the biggest that it could be. Okay. Now, I do want to be careful. I'm going to go ahead and plug in the positive number right here. And then for x, that was 3, and dy, I'll plug in a positive 0.05. In this case, that works out very nicely because my two partial derivatives were both themselves positive. Okay. But if one of them had been negative, I would have wanted to then plug in the negative value for the corresponding differential. Because what I want to try to avoid is having this error, which is the error because I got x wrong, and this error, which is the error I got because I measured y wrong. I don't want them to cancel out. It is entirely possible that I measure x too big, but I measure y too small, and those errors balance out, and I get exactly the right area. Lovely. I did things wrong, and I got the right answer. Okay, that can happen, but if we're asked to approximate the worst case scenario, we don't want our errors canceling. So we want to ensure that we've got the same sign for both of these things before we take the absolute value. And then we're just talking about the amount of error, not error as a signed quantity. We're saying we could be this much over, we could also be that much under. That's just the amount of error that we could have. Okay, so I ensured that both terms here were positive. Okay, and then this would become the absolute value of 0.5 plus 0.15, which would just be the absolute value of 0.65, which would be 0.65. So we would estimate that the maximum amount of error we could have in the area would be 0.65 square inches. What I essentially did when I made sure that these two pieces that were contributing to the differential, which was our error, had the same sign, is I was using something that's called the triangle inequality. And it just says the absolute value of A plus B. I know it's not the absolute value of A plus the absolute value of B. Absolute values don't distribute over addition. But this will be less than or equal to the absolute value of A plus the absolute value of b. I will have equality when, as in this case, both terms have the same sign. So then when I add them and take this absolute value, it's the same thing as if I took the absolute value and added them. But I will have it's less than if these two things have opposite signs. So that would be what we were trying to avoid, of one error that was positive canceling with another error that's negative. Okay. So when you are approximating the maximum error, okay, you can either sort of rig it so that you're making sure that both things are positive, or what I think actually makes more sense to do is to just plug in the absolute values for the differentials, and then say that's less than or equal to the absolute value of 0.5 plus the absolute value of 0.15. Just explicitly use the triangle inequality there. That way, if you did have a negative from one of your partial derivatives, you're going to be taking the absolute value before you add, so you're making sure that these pieces are both positive, and you're getting 0.65. Okay. All right, again, the book sort of glosses over that. They just sort of plug in the worst case scenario, but I believe in the examples that they work out, they're kind of like this one, where the two partials do have the same sign, so that you're not forced to think about the issue of what if they were going to cancel each other out. I do want you to pay attention to it. They could cancel each other out, so make sure that both pieces have the same sign, and I think the easiest way to do that is to simply use the triangle inequality. Just write what you get for the partials, take the absolute value of your differentials and plug those in, and then use the triangle inequality to simplify.